Welcome to General Structures 2 and Lateral Forces, lesson 4 quiz, question number 3. And it says, select the incorrect statement. And we'll go down each of the letters A, B, C, and D and to say why they were correct or incorrect, and then go ahead and find out what our answer is. Alright, A shear wall resists lateral forces in its own plane. That sounds correct to me. Sounds correct. I'm guessing that a shear wall, it's right here, it's going to resist, this is in its own plane, saying this is your XY plane. Y. So it's anything that makes up this square in that XY plane. So that's in that plane, it's going to resist forces in that plane. That is correct, and therefore is not the answer we're looking for. Alright, going on to letter B. A concrete diaphragm distributes horizontal forces in proportion to the rigidities of the vertical resisting elements. That's a little bit difficult to wrap your head around, so I'll read it again. Concrete diaphragm, fair enough, distributes the horizontal forces, okay, in proportion to the rigidities of the vertical resisting elements. And that sounds correct, so I'm going to go ahead and mark it off. And the best way I can explain this is to use a bridge reference, because that's mostly what I do. Alright, so here's my bridge reference. You have a bridge right here. Then here's, let's make it green as your ground line. Right here. And that might not be the best ground line to do. Let's do this. Ground line drops off the river down here. And then it comes up like so. Alright. So here's an abutment, or one end. Here's the other end. And let's say you made it well, let's say for some reason you have to do this, which you wouldn't want to do. But you have to do something like this. And these are your spans. Alright, hopefully you understand what I'm saying here. This is your bridge, it's your superstructure. And it comes across right there. Let's say for some reason, which this is not a realistic situation, but you would make this continuous over each of these supports. In that case, and not only are they continuous, but these are also integral. So you're casting these in, which once again, you would not do in real life. You wouldn't make something like this. Well, you might. I might want to say wouldn't, but you go ahead and you're going to cast this so it's all integral. This is the integral end bit. And when I say integral, that means that there's reinforcing and whatnot to make it. So this bent's going to see any lateral forces or transverse forces into the screen. So if I put wind into the screen, like wind blows this way, not up, that's kind of hard to just show, or into the screen, going that way into the screen, it's going to blow on that bridge. It's going to go into the screen. It's going to want to throw the bridge that way. So that bent's going to see that force, and that's going to see the force. Anyways, in designing bridges, you have this, I don't want to say temperature forces because that might be confusing, but that's usually what will control. You have a car or a truck, let's say, and that truck is going to stop. You have braking and you have traction forces, and so when that car stops, you can think about it, it's going to transfer that momentum and that force down to the superstructure, and that's going to go down to these individual bends, which we'll call them. Because this is end bent 1, this is bent 2, bent 3, bent 4, bent 5, bent 6. So that didn't work out so well. There we go, bent 6, and bent 7. Right, let's call it end bent 7. And since this is all one unit, this is one structure, you're not making this an expansion unit, and therefore you're not going to see these transverse forces. So you have to end up, well, I mean, if I stop right here, am I gonna, is this every single, if I have a load right that goes right there, is every little bit of that load going to go into this bend, or how do you take that load and, well, how much is it? 90% of this bend because it's closer, maybe 10%? Is it 50-50 between bent 2 and bent 1 because it's in that span? And the way it turns out, and the biggest way what you'll come up with if you ever do this is you'll come up with your temperature loads are the biggest problem. So this longitudinal forces usually aren't huge, but if you get long spans, these temperature forces, I mean, they look at it and they say, oh, that's 600 foot of temperature force. So let's say you have 600 foot times, rule of thumb is an inch per 100 foot. So 600 foot this is going to expand 6 inches. Now, is that really going to happen? You could make an argument either way, but that's the rule of thumb. So this bridge is going to expand 6 inches somewhere. Well, where? Well, it all depends on how stiff this end bend is. And you can have a dead man anchor on this to help pull. So in other words, when this heats up, the temperature gets higher, let's say, this is going to push out. And when the temperature goes down, it's going to want to suck in because the concrete will contract. So, once again, without getting, I'm getting away from it. Back to here. So that's the issue we have. How do we distribute those loads? Well, we have to get a point of centroid of where it is, and that's going to be difficult to do. Let's say the point of no motion is right here. And because this is so tall, it's actually going to bend easier, and it's going to be less rigid than these short ones. So you'll find out that these shorter bends will end up taking a lot more. Let's say this is a pile or this is a shaft. These short ones will see more of that longitudinal load than this tall one is. I don't know if that's intuitive to you, but if you really think about it, take a ruler and then take something stubby. Or what you could do is take, think about it. You have a rubber band. If you have a rubber band right here, and you have a pencil, or let's say go something even more. You have I don't know, let's just say a pencil, a rubber band, a pencil, and you have something that connects the two of them that's rigid, and you push on it. Is that rubber band going to accept any of that weight? No, because it's really, really flexible. This is going to take 100% of that weight, or that force. All right, so I think I've gone a little bit overboard on that. Hopefully that didn't confuse you too much. If it did, just ignore me. And remember that the more flexible something is, the less force it's going to take. If it has a path to take where it can be more rigid, it'll take that path first. So in other words, this is a correct statement. Back to going around. In proportion to the rigidities. So yes, the more rigid something is, the more force it's going to take in proportion. So I'm going to say yes, that's correct, and we're going to move on. C, a plywood diaphragm distributes horizontal forces to the vertical resisting elements in proportion to the tributary area of each element. And that's also correct. And this is the key word here is plywood diaphragm. Because it's plywood, you don't calculate the rigidity of the plywood diaphragm. You do this for concrete. So that's just something, hopefully that comes naturally to you to remember that, but that's something I would just remember. So that is also a correct statement, and I encourage you to look back in the study guide to see if it makes sense to you and read that over and justify that to yourself, what I just said. So I'm going with the answer is D, and let's see why this is incorrect. D, torsion is the rotation that occurs in a diaphragm when the center of mass does not coincide with the centroid of the building. And this sounds pretty good. If you just take a look at that and didn't study any of this, you would say, oh, well, yeah, that sounds fine. If the center of mass does not coincide with the centroid of the building, yeah, it's going to create a torsion. But the key thing in here is the centroid of the building, and this is incorrect. It's actually the center of rigidity. It's not the centroid of rigidity. It's the center of rigidity. All right, and that is why this is the incorrect statement, and D is your final answer. I will see you on question number 4.